So we come to the fourth lecture of Keith's course. So Keith.
Yeah, thanks, Bala. Yesterday I went through a whirlwind express review of gravitational wave emission from a binary in-spiral merger. Today I want to start looking at gravitational wave emission from a single star. Whether the star is isolated or in a binary, the fact that it's spinning can give us gravitational wave emission. Now this will cover some of the same ground that Alicia covered, I think, yesterday. But I think a little bit of repetition here is okay because this is material that you really want to have well in hand. So let's begin with the basics, and I'm going to focus initially on the relatively simple model of mass quadrupole emission, and then we'll look later at R mode emission, which is a more complicated process. So let's consider our canonical model of a triaxial star, where we say the spin is defined to be along the z-axis. So we imagine some star that wouldn't exaggerate the oblateness for a typical star. We would have an x-axis, say, this way, and we'd have a y-axis into the board and a z-axis this way, and the angular velocity vector is along that z direction. And this is not a sphere. It has some oblateness because it's spinning, and it may have some additional asymmetry. We hope it has some additional asymmetry to it. And so we're going to make the assumption that the moment of inertia around the x and y axes are going to be very comparable to each other, but hopefully with a slight difference, and they're both less than the moment of inertia iz around the spin axis because it's an oblate star. It has a poloidal ellipticity naturally. What we really care about is what we call the equatorial ellipticity. Now, in principle, when you have this kind of a model, you could have a misalignment between this angular velocity vector and the angular momentum vector. So you could, in principle, have precession of this object. And in that case, you would have gravitational radiation emitted at a gravitational wave frequency of both the rotational frequency and twice the rotational frequency if we had a precessing star. And so let me initially consider that possibility, and then later I'm going to dismiss the case of FGW equal to F rotation, because we normally don't worry too much about that. But if you look in this famous paper, sorry? Oh, it could change a little bit, but this is a starting assumption. But let me present the model from JKS paper as a specific example. So in the Jaranowski, Krolak, Schutz paper, famous JKS paper in 1998, which in some sense serves as a so-called Bible for our community because it sets out much of the nice framework we use. We imagine a star with an angle theta between the angular momentum vector and the symmetry axis. And with an inclination angle iota, always end up with the dot on to call it an I, but it's really a Greek letter, iota, between J and the line of sight to the observer on the Earth. And in this model, we have several different components to worry about. One of these is called H1 plus of t, and it's given by 1/8 H naught sine of this angle 2 theta, sine of 2 iota, cosine of a phase function psi of t, and the plus refers to the plus polarization that Alicia's described before, and then we have a cross corresponding term, a counterpart, that is 1/4 of H naught sine of 2 theta sine of iota, and the sine of that same phase function. And this is a radiation for which the gravitational wave frequency is the same as the rotational frequency. So in this model. There's another set of contributions called H2 plus of t. And I think this is an explicit model that Alicia presented, where we have 1/2 H naught sine squared of theta, 1 plus cosine squared of iota, and then cosine of 2 times the same phase function, psi of t. And then we have the cross term, not sine squared theta, and then we have simply cosine of iota and the sine of twice that same phase function. And of course, these two terms correspond to FGW equals 2 times F rotational. And in general, our detectable signal will be a mixture of these. And in some of the recent searches from the LVK, we have conducted searches for both of these for known pulsars. We look for the possibility that a star, a known pulsar, is emitting radiation at both of those frequencies. But the detectable signal in general is going to be H of t equals H1 plus plus H2 plus times the corresponding antenna pattern function, in addition to H1 cross plus H2 cross times its corresponding antenna pattern. And of course, those depend on time. Just as a reminder, F plus and F cross are the time-dependent antenna factors, and I believe you had some exercises already calculating such things. So I won't belabor that point, but you do have to remember that they're there. And they play an important role in the searches as Alicia's described. I guess there's different ways of thinking about it. In some sense, it's allowing for complete generality of your model. You have a triaxial system that is rotating. You're looking for a change in the reduced inertia tensor that I presented a day or so, or yesterday, I guess. And so you're looking for anything that would lead to a signal at either one or twice the frequency. So it's not the model we focus on normally. Now I'll talk about that in just a second, but this is a general model. It's allowing for the possibility. Well, that's a good point, because it's not necessarily the z-axis. I'll come back to that point in just a second. This is a more general statement. I chose a particular axis, set of axes there for my own purposes, but this is somewhat, in some sense, more general than that. Okay, so in practice, we think, and because we're not sure, we also do these searches for FGW equals F rotation for known pulsars, but in general, we don't think that the FGW equals F rotation term is needed. And the reason for that is we don't think that the associated precession actually happens very much at all, if at all. I talked about that in the context of electromagnetic observations of pulsars. We just, we have 3,600 pulsars and maybe a few that may be showing signs of precession. It's not a common phenomenon. And there's good reason to think that there's actually gravitational wave emission that would tend to damp out such precession. If you had an oblate M&M sort of a thing that's oscillating around, that will emit gravitational radiation, but it tends to very quickly damp itself out. Their dissipation terms, they'll tend to bring that wobble angle, as it's called, back to zero. And so you very rapidly get rid of that precession. At least that's what we think is happening. Now, in the context of this particular formalism, the way we handle what we think is actually more relevant is to set this angle theta equal to pi over 2, and that automatically gets rid of these extra single rotation terms. And so we end up with H1 plus and H1 cross equal to 0. And we just don't worry about them anymore. And what I'm going to present from now on, I'm not going to worry about the possibility that there might be first a single rotation term. Yeah. Yeah, I'm only talking about the essentially the LA2 terms. I'm not worrying about higher order modes. That's right. It's a very simplified model where you just have these inertial axes, and we're not worrying about. There are, but depending on how complicated the structure of a star is, you could have higher order modes. But you can think of this as being like a triaxially ellipsoid, in which case it's relatively simple. Okay, so with that in mind, we will say that H plus is really just H2 plus, and we have H naught in a more concrete model times 1 plus cosine squared of iota over 2 times cosine of 2 times omega times t if we had just a simple spinning star without any frequency derivatives. That's just a crude model. It gives us an idea of what to expect. And then we have H cross being just H2 cross, and that's H naught cosine of iota times the sine of 2 omega t. But again, we must include omega derivatives in general. But just if you're asking what's happening instantaneously, this is a good way to think about what you're seeing instantaneously in the detector. Now that H naught, describing the amplitude of the signal, I think Alicia may have given you this expression already, 4 pi squared times g times epsilon times IZ F GW squared over c to the 4th and the distance d to the source. And so just putting in some numbers, 1.1 times 10 to the minus 24 times epsilon over 10 to the minus 6. I'll come back to that choice in a moment. Times IZ over a nominal value, I naught. That's very commonly used in the literature. FGW over 1,000 hertz squared. And then we have a distance, which I'll take in this instance to be 1 kiloparsec. So if I have ellipticity of 10 to the minus 6, I have a nominal moment of inertia, I naught, and my gravitational wave frequency is a kilohertz, so 500 hertz rotation frequency, and I'm at 1 kiloparsec away, then I get about 10 to the minus 24. Now, by modern standards, that's a pretty loud signal, 10 to the minus 24. We routinely get below that in our sensitivities. Now this epsilon parameter, I think we should introduce that also, is the difference between Ix and Iy divided by Iz. So this is known, it's usually just used, we normally just call it the ellipticity, but strictly speaking, it's the equatorial ellipticity to distinguish it from the poloidal ellipticity associated with the oblateness of the star around its spin axis. And this I0 parameter is arbitrarily, but somewhat reasonably well motivated, chosen to be 10 to the 38 kilogram meter squared. But be aware that there's easily an order of a factor of 2 uncertainty on what the true I0 is. Depends on the equation of state, depends on the radius of the star, of course it depends on the mass of the star. This is just a handy benchmark that you'll see it used quite a bit in the literature. But be aware that this assumption will often affect the values of derived quantities you'll see in a paper. Okay, so with that model, the total gravitational wave luminosity the EDT, which is really minus the luminosity, becomes minus 32 over 5 G over C to the 5th IZ squared, epsilon squared, omega to the 6th. And just to put in some numbers, just for reference, that's minus, for a particular choice, minus 1.7 times 10 to the 33 joules per second. Convert that to ergs per second if you like, times Iz over I0 squared epsilon over 10 to the minus 6 squared. And then we have, again, a choice of a kilohertz gravitational wave frequency raised to the 6th power. Okay, so that's the luminosity. Now we can do the same sort of thing we did for magnetic dipole emission and say, let's equate that to the loss in rotational energy. And if we do that, we get that the first derivative of the gravitational wave frequency is given by minus 32 pi to the 4th over 5 G over C to the 5th Iz epsilon squared times F GW to the 5th power. Okay. So the first derivative is proportional to a negative constant times the 5th power of the gravitational wave frequency. And so from that, going back to our original discussion, we conclude that the breaking index that applies to this kind of emission, to this mass quadrupole emission associated with the equatorial ellipticity, that breaking index is 5, as opposed to 3 for magnetic dipole emission, and as opposed to the 7 that we'll see later for R-mode emission. Okay, so given what we saw before, for an arbitrary power law spin down, we can calculate a nominal lifetime. And so we get from the same procedure as before, tau equals FGW over, in this case, minus 4 FGW dot. The 4 comes from n minus 1. And then we have this correction term that depends on the relationship between the current gravitational wave frequency and whatever it was at the birth of that star. And that correction goes like the 4th power of that ratio. But as usual, we can say that if it's the case that the current gravitational wave frequency is much less than what it was at the outset, we're trying to estimate the age of the star, then really we just get FGW over minus 4 FGW dot. Of course, FGW dot is negative. So notice that this is half of the magnetic dipole term, where we had a factor of 2 instead of 4 in the denominator. So this calculation assumes a gravitar model where we have a star that is spinning down either solely or dominantly by gravitational wave emission. So either it's a pure emitter or it's so dominated by the gravitational wave emission that we can make that approximation. As I say, we can neglect any spin down due to magnetic dipole emission or other contributions. But in the general case, that's not what we expect. We expect mixed emission because many of the stars that we expect to give us gravitational wave emission also have magnetic fields and they're spinning fast, so we expect at least some contribution from magnetic dipole emission. And so in general, when you have that mixed model, the fraction of F dot that is due to gravitational wave emission tends to get reduced with time as the frequency spins down. Assuming that you are fixing the ellipticity and that perpendicular component of the magnetic dipole moment, or the magnetic field at the pole, if you like. And so if you imagine plotting as a function of the logarithm of time, the logarithm of the frequency, then what you would expect is initially you don't have a dramatic change in a log scale on this frequency. So initially it looks a little bit flat, but then you enter a region here in a particular model where you would have gravitational wave emission being dominant. And for that, we would expect a slope equal to minus 1/4. But as the frequency comes down and down and down, then the relative importance of the gravitational wave emission has to get smaller compared to what it was before relative to the magnetic dipole emission. And we expect a turnover so that we transition into a slope here where the magnetic dipole emission is dominant. And in that regime, the slope will be minus 1/2. Let me show you a numerical simulation of that. Make sure I get the right slide there. Here we go. So this is actually something you'll do as an exercise, I guess today. Is that right, Ankur? Today? Yeah, thanks. So you'll try to reproduce this, essentially this graph. I think it's the same set of parameters. This is a very extreme case where I have a star that, unfortunately, that bar is blocking the title of it. Oops. Yeah. Oops, there we go. Okay, well, anyway, the title on the plot has more information, but it's assuming a magnetic field of, as you can see, 2 × 10⁻15 Gauss. So it's a magnetar, which we expect to spin down really fast. At the same time, I've given it an extremely high ellipticity of 0.03, if I remember correctly. And so you've got two things that are both two effects trying to spin the star down really fast. And so the time scale over which you get a dramatic change in the frequency is only about 10,000 seconds. So it shows a relatively extreme set of parameters, but I wanted you to be able to see this transition from gravitational wave dominance to magnetic dipole emission dominance You try verifying this numerically. Okay, so in those benchmark numbers I showed you, for example, for the strain amplitude, I said let's take a value of epsilon of 10 to the minus 6. Now that turns out to be a pretty optimistic assumption. It's not crazy, and we think it is. It is, in fact, possible to have stars with that kind of ellipticity, but it is an optimistic scenario. So let's ask what that would correspond to. So what does epsilon equals 10 to the minus 6, which is really big, be realistic about it, what does that correspond to? So just as a toy model, let's assume we have a uniform density model for a triaxial ellipsoid. Having semi-major axes A, B, and C, say along the X, Y, and Z axes. So in that case, IX has a moment of inertia of 1/5 times m times b squared plus c squared. IY is 1/5 m times sum of the squares of the other two terms, and then likewise IZ is 1/5 m times a squared plus b squared. Of course, if you were to look at a sphere where A and B and C are all the same, you end up with a more familiar 2/5 mr squared moment of inertia. Okay, so in this model, the equatorial ellipticity, epsilon, defined to be Ix minus Iy, sometimes it's Iy minus Ix, but it doesn't really matter, over Iz, that becomes b squared minus a squared over a squared plus b squared. But now we're really talking about a case where a and b are almost the same value. We're talking about epsilon differences. I shouldn't use the word epsilon, but the letter epsilon, but a small difference. So let's assume that b, in fact, is equal to a plus some small delta, where delta is much less than a, which is surely the case. In that case, epsilon is of order b minus a over a, that is to say delta over a. And so the ellipticity is basically linear in that difference between b and a in this model. So we can plug in some numbers for an ordinary conventional neutron star and get a sense of what the ellipticity of 10 to the minus 6 actually corresponds to. And so for A in the ballpark of 10 kilometers, epsilon that is equal to 10 to the minus 6 corresponds to a delta of about 1 centimeter. Now I should remind you that this is the height of a stellar bulge, not some local mountain. And so if, for example, you were to go in and create yourself a little mountain on the surface of the neutron star, some little dimple, that's not going to qualify. You need to have something that is global on the scale of the whole star in order for it to give you this sort of ellipticity. But keep in mind that we think that this deformation is going to primarily be in the crust. And the crust is much less dense than the core. This toy model assumed a uniform density throughout the star, but the crust is definitely less dense than what's in the core by a lot, depending on how deep in the crust you have this deformation. And so that requires, for the same ellipticity, a larger bulge. So something bigger than 1 centimeter. Oops. And of course, that depends on whatever your assumed equation of state is. All right, so let's talk about some potential sources of the asymmetry that gives us a non-zero epsilon. So potential sources of, say, an XY asymmetry. This is not an exhaustive list, but some key possibilities. One is crustal cracking from the cooling of the star, or its spin down. Both of those will tend to lead to changes in the shape of the crust, particularly the spin down, because we have a star whose ablateness depends on its spin, and as it spins down, that solid crust has to keep adjusting to the internal shape of the core, which is getting less and less oblate. And so, that leads to the possibility of cracks forming in that process. So you would expect there to be, at any given moment, some elastic strain just due to the fact that they're spin down, and then the cooling introduces an additional factor. Another possibility, I'll come back to a little bit later, is a buried magnetic energy asymmetry. Remember, any form of energy is equivalent to mass, and so if you have little hot spots, so to speak, of enhanced magnetic field energy due to some stochastic mix of magnetic fields underneath the surface, then that too can lead to an asymmetry. And you can think of this as being a magnetic strain on the star. And another possibility, I'll come back to a bit later, is accreted matter from a binary companion. And you could argue this is actually the most promising possibility, because here we have a source of mass raining down on the star, and it might well deposit itself in a non-isotropic way. And I'll come back to that point later on, hopefully toward the end of today's lecture, possibly the start of tomorrow's lecture. Okay, so clearly the elastic strain in the crust depends on the history of the star. If we wanted to be able to predict what it's going to be in the future, we need to understand how the star evolves as it both cools and spins down. So the elastic strain depends on the stellar history. One thing to keep in mind, to keep you from being too optimistic about things, is that the cracks that could form from this cooling or from the spin down itself, those cracks will tend to anneal with time. Because, speaking in a Newtonian framework, there's an enormous gravitational field. this is nothing like, say, an asteroid in our solar system. You've probably seen pictures, satellite pictures of these asteroids flying by with all kinds of weird oblong shapes. That's because they don't have much gravity to try to pull them into a spherical shape. But here we're in the other extreme, about as extreme as it gets, and still having matter present. So we can estimate an upper limit, not necessarily a realistic value, but an upper limit from basically energy minimization and an assumed breaking strain. It's really just an order of magnitude estimate, but it's useful as a benchmark. The breaking strain, U break, is a dimensionless quantity. And you can just, back of the envelope, estimate that the maximum ellipticity you might possibly optimistically expect would be in the ballpark of a quantity mu times the radius of the r squared times delta r, I'll explain these terms in just a second, over gm squared over r times this breaking strain U break. And in fact, let me simplify this by just calling everything in parentheses a parameter B. So B times U break. Now the parameters I've introduced here are, first of all, mu is the shear modulus for the crust, and delta R is the crust thickness. Remember, this is where the elastic strain is applicable. We need to have a solid crust for that to even matter. Otherwise, we have a liquid. Oops, this is crust thickness. And this parameter B, this shorthand, is known as the rigidity parameter. And it's, roughly speaking, the ratio of the maximum crystalline lattice energy that is governed by that shear modulus parameter divided by the gravitational binding energy. So again, this is just an order of magnitude estimate of what you might very optimistically expect would be possible. And that ratio, we think, is in the ballpark of 10 to the minus 5 for realistic equation of state for that crust. And so from that, we would conclude that the maximum ellipticity that we might hope for is of the order of 10 to the minus 6 times B over 10 to the minus 5. And again, B of 10 to the minus 5 is not crazy. And then U break could be as high, believe it or not, as 0.1. You might naively expect that to be a very optimistic overestimate, but there is actually some support for that notion. So U break, the breaking strain as large as 0.1, is actually supported by some molecular dynamics simulations. So these are just numerical simulations, but done in the same way that these sort of things are done in condensed matter physics, but applying it in this very extreme realm. And so at least the initial result looks pretty good based on these simulations, but I should caution that at the same time, these simulations were done on essentially microscopic time and distance scales, just because of the computational cost of doing such simulations. So we don't know for sure that this would hold up. If you could do the simulations 100 times longer or expand the dimensions factor of 10 or more, whether they would really hold up. The worry would be, for example, that you would get plastic creep of this crystalline lattice that would reduce this value. Okay, now let me talk about magnetic field contributions to possible asymmetries. So we can have magnetic field asymmetries. But again, we can use energy scaling arguments to estimate upper limits on. So one scaling would be, if you look at the ratio of the magnetic energy associated with, say, a dipole field in the volume of the star, sort of a calculation you've already done, divided by gravitational binding energy, then you get values in the ballpark of 10 to the minus 12 times B over 10 to the 12 Gauss squared. And 10 to the 12 Gauss is, in the right ballpark for a typical pulsar. Not a magnetar, not a millisecond pulsar, but a relatively young star. Okay, well, that doesn't look too promising. Because I gave you benchmarks assuming epsilon of 10 to the minus 6, and those were accessible by present-day interferometers, and epsilon of 10 to the minus 12 is not at all accessible today or even with third-generation detectors. So that's not a great scenario to count on. So this is not promising. But another possibility that might actually be realistic is the contribution from a toroidal magnetic field buried beneath the surface. There's actually good reason to think that such a field could get wound up by this rapidly spinning neutron star, and so you end up with a buried magnetic field that is actually quite strong. So in this model, you could have ellipticities as high as something like 10 to the minus 9 times a magnetic field strength at 10 to the 12 Gauss visible on the outside. So the assumption is that the field inside is actually significantly higher than that and is creating asymmetries as it's wound around the equator of that star. Okay, so these are, some sense ballpark, back of the envelope estimates of what you might optimistically hope for, but you can also ask, well, what does the data actually look like from known pulsars? We have a lot of information about known pulsars based on their timing. So what does the pulsar population actually suggest about actual epsilon values? Because it turns out we already have quite a bit of information from the pulsar population as to what is possible. We can basically place an upper limit on the detectable strain, using a gravitar model, and observed F and F dot values. And I think Alicia showed you how to derive this yesterday. We can derive a limit on the possible strain of a known pulsar as being 1 over the distance to the star times the square root of minus 5 halves g over c squared moment of inertia I is z times f GW dot, which remember is negative, over f GW. And if I plug in some numbers, you can get a sense of what that scaling looks like. I'm sorry? In this expression? I'm sorry, I don't think I have a delta, but maybe my handwriting is so bad that it looks like a delta. Oh yes, this is the same model that Alicia presented yesterday, where you assume that all of the spin down energy, all of the rotational energy loss is due to gravitational wave emission. So this is yeah, that's a good question. I should have pointed that out. So this is an optimistic gravitar model. Where just as we did before, we ascribe all of the rotational energy loss to gravitational wave emission, and ask, well, under that assumption, then what would be the strain? The actual strain will be less than that in general. Okay, so if we plug in some numbers, then we get 2.6 times 10 to the minus 25, which is still a pretty big value by modern standards of searches, times 1 kiloparsec over the distance to the source, 1 kilohertz, oops, over FGW, minus FGW dot over, I'll choose 10 to the minus 10 hertz per second, and then IZ over our nominal value I naught that I gave you earlier, all of that raised to the 1/2 power. Okay, so again, that gives you some sense of what you might expect under these assumptions. All right, so with that formula, I can actually look at the pulsar population and see what it looks like. What is conceivably possible? So that's what the pulsar population looks like. This is nearly all the ones we know about. And this is a different way of plotting the same ones I showed you yesterday on a P dot diagram. This is now frequency on the horizontal axis and the spin down that's shown on the board on the vertical axis. And just for reference, there are some diagonal dashed lines indicating values of the ratio of epsilon over d in units of inverse kiloparsecs. But all of these dots and triangles refer to specific known pulsars for which we actually have measured values of F, rotational F, and the spin down of that, and those have been translated here into twice that for the gravitational wave frequency. And the curves I've shown here are sensitivities that you might expect with 3rd generation gravitational wave detectors, Cosmic Explorer, Einstein telescope. The advanced LIGO curves would be up here somewhere, actually a little higher than that, in this region. And the main thing I want to point out is that in principle, at least for 3rd generation detectors, and also to a much lesser degree current generation detectors, some of these stars are in principle accessible. We have strain sensitivities that are below spin down limits. But again, the spin down limit is a very optimistic assumption. The gravitar assumption, which is almost surely not applicable to most of the known pulsars, which most of them show evidence of having at least a significant component of magnetic dipole emission. I'll note that the very first one we beat the limit for was a crab, way back in the initial LIGO days. And then when Virgo turned on, we beat Vela's limit because Virgo had better sensitivity than LIGO at the end of the initial LIGO-Virgo era at low frequencies. But then more recently, we started beating the spin down limit on millisecond pulsars. And currently, I believe we beat the limit on 23 in total from the 01 through the 03 runs. So we're in the ballpark of 20. We expect that by the end of the 04 run, that number is going to increase by an amount. I can't quote you a number, but it'll increase by the time we're done, but not as dramatically as you would get from a third generation set of detectors. One thing to point out is that because, I guess I have the formula here somewhere. Maybe I've already erased it, perhaps. Okay, well, you might recall that the strain that you get depends on the ellipticity linearly, but quadratically on the frequency. And that means that when you're looking at strain sensitivity that's not that different from low frequencies to high frequencies, less than an order of magnitude, you get a dramatic improvement in your ellipticity sensitivity by going to higher frequencies. I'll come back to that point in just a moment. But depending on whether you prefer young stars that are spinning down and have lots of potentially residual asymmetries, perhaps glitching, or if you like those nice, stable, high-frequency millisecond pulsars that give you a nice F-squared enhancement in your strain, but which have had a lot of time to anneal, you might prefer this region of the diagram, or you might prefer this region, depending on how you tailor your searches. At least you may talk about that also. So let's now isolate the ellipticity and focus on that very specifically, keeping in mind what I just noted about the scaling versus frequency of strain amplitude. Actually, I didn't need to get off the, let me just, I'll note that down. Let's now isolate ellipticity using the same sort of formalism, and I'll spare you the formula that goes with it. Let me go back to my slides. Apologies for this. And let me go to the next slide, which shows the same set of stars, but now the vertical axis is a corresponding upper limit on possible ellipticity, again, in the gravitar model. And in this diagram, it's more apparent that we gain a lot by going to high frequencies if we want to go down in ellipticity. So earlier I said that ellipticity of 10 to the minus 6 is possible, probably, but not necessarily expected. The more realistic estimates of what is expected are much smaller than that, orders of magnitude smaller than that. So we probably want to be in this region of the graph, above several tens of hertz in order to get ellipticity that's below 10 to the minus 6. Now the blue asterisks indicate what you see based on the measured F and F dot of that star. So that's already an upper limit. And then these green vertical lines show you the range you could expect with third generation, in this case, Cosmic Explorer, sensitivity for basically a match filter search, the very best you could do if you followed a star and knew its ephemeris accurately. Of course, that is realistic for a known pulsar. We do that all the time for of order 200 stars already. So if you want to get down below 10 to the minus 6, you probably want to focus in here. And there are some arguments that would really keep you in this range here, around 100 hertz or so. based on the likely evolution of stars in the galaxy. I don't have time to talk about that, but just be aware that as promising as it might look out here for the millisecond pulsars, it could well be that our most promising source is a younger star with a gravitational wave frequency in the ballpark of 100 Hertz. In fact, I'll come back to that point for a different reason later on. Okay, so we can see from this graph that we have a drop-off in sources with ellipticity. Oh, yeah, that's actually another point I should make very explicitly. So if we look at this graph, this is 10 to the minus 8. This is 10 to the minus 10, so 10 to the minus 9 is right here. You'll notice that there are only maybe 2 or 3 blue asterisks below 10 to the minus 9. That's not a selection effect. There are, it should be possible to find stars below here if they exist. Falling below that line does not necessarily mean that you've crossed the death line. You can still be pulsating and still have an ellipticity below 10 to the minus 9. So the fact that we don't see that is suggestive, at least if you're an optimist, like those of us in the continuous wave community tend to be. So we have a noticeable drop-off in the sources below 10 to the minus 9 for this spin-down value based on what we see in the current population of more than 3,000 pulsars. And as far as we can tell, that is apparently not from hitting the pulsar death line. Or to look at those same stars that are in the vicinity of 10 to the minus 9, if I look at them on a PP dot diagram, they're not all sitting right near the death line. They ought to, stars like them ought to just keep going for a while longer. And so this is suggesting a possible, an exciting possibility that there might be a minimum ellipticity at the level of 10 to the minus 9, and that is contributing to the spin down of these stars. And perhaps it comes from that buried toroidal magnetic field I alluded to earlier. We don't know what it might come from, but there has been a nice paper by Wone et al. That's looked at this possibility and finds that it is plausible. Again, maybe we're all just being optimists. And epsilon of 10 to the minus 9 is actually, as you saw from that graph, something that we can easily achieve in a third generation detector and which we can approach with current detectors. We're already at the ballpark of 10 to the minus 8 in O3 searches, and we're going to do better in O4 and then O5. Okay, so let me talk about another type of emission known as R modes. So far I've focused on quadrupole mass emission, due to mass asymmetry, and that's analogous to electric quadrupole emission in electromagnetics, electrodynamics. Now I'm going to talk about another possible contributor to gravitational wave emission, which is a current, a mass current quadrupole that in some sense is analogous to a magnetic quadrupole emission. I'm not going to talk about some of the other modes you may occasionally encounter in the literature, for example, F modes. F modes are something that we think do happen and could be important in the very final stages of a binary neutron star merger. But F modes, these are radio modes of oscillation of the remnant. They tend to damp out very fast. So they're not particularly relevant to continuous wave emission, although they may be relevant and may be very interesting to see as we improve the sensitivity of our detectors at very high frequencies. So they happen around 2 kilohertz or so. But I'm going to focus on R modes because those are the ones we think are most promising beyond the mass quadrupole emission I've already talked about. So as we commented before, a neutron star has, in some sense, a neutron fluid, and some of that fluid is in a superfluid state. That superfluid motion in the neutron star is analogous to electric currents. And it can lead to emission if that pattern has a time dependence to it. Now, R modes in particular are susceptible to amplification by what's known as the Chandrasekhar Friedman-Schultz, Friedman-Schultz instability. This is also shorthand as a CFS instability. These R modes are analogous to what are known as Rossby waves in our own atmosphere. They actually have quite a bit in common. As I say, the jet stream in the Earth's atmosphere. Does the jet stream play much of a role in the weather here? The weather's pretty stable and constant, isn't it? Yeah, okay. In the northern latitudes, the jet stream is very important. It causes enormous fluctuations in our weather. So let me draw a crude diagram. So you imagine a current that is nominally toroidal, but is subject to Coriolis forces. That gives you a wave in a toroidal current. So imagine you have a angular velocity vector that's turning this way, but you have a current that could flow in either direction. But let me focus on a wave pattern that flows in retrograde. So we have a wave that is formed in this toroidal current. And so that wave is a time dependence in the current quadrupole, well, I should say the mass current pattern, and it leads to radiation. If the current just flowed around in a toroid, and we're not bent around like that, then you wouldn't expect any radiation from it. So the instability arises in the following condition. The instability arises when the rotational speed of a star is higher than the propagation wave of the propagation speed of the wave. Oops, sorry. And in particular, the condition that can happen, actually relatively easily for R modes and reasonably fast spinning stars, it's high enough that retrograde propagation that is retrograde in the neutron star rotating frame can actually be prograde as seen by a distant observer. So you have this wave pattern that's trying to go around opposite the rotation direction of the star and is seen by someone on the star as being retrograde. But if you're looking at it from a distance, you say, well, no, actually it's going around prograde also. It's not keeping up with the rotation. And so a consequence of that is that if you have a loss of the retrograde neutron star frame angular momentum, because the gravitational waves emitted carry away angular momentum, then that change is actually a gain in the prograde angular momentum as seen by an inertial observer. It's a very non-intuitive effect. It's thought to be real, and it leads to an unstable amplification. That increases rotational speed a little bit, but more important, it increases the wave amplitude. At least until saturation is reached. And that saturation is dependent, as you might guess, on dissipation effects. So that saturation is governed by dissipation that we don't really understand very well. There have been a number of papers arguing both sides, in the sense that some papers argue that the dissipation is actually quite substantial. This amplitude would never get very large, and then other papers have argued, well, no, actually that dissipation doesn't apply in reality, and the amplification can be quite large. In any case, whether we have a high amplitude or a low amplitude, the radiation that we expect to see in a distant observer frame is at a gravitational wave frequency that is approximately 4/3 of the rotational frequency. Now that, you should keep in mind, is actually a low spin, low frequency approximation. So you'll often see a reference to the 4/3 factor, but be aware that it actually has a substantial potential correction to it. And that correction matters a lot if you are trying to use a known pulsar and you're trying to use known pulsar ephemerides. It would not be safe at all just to assume 4/3 for that factor. And so, more explicitly, this mode is expected to look like minus L minus 1, L plus 2 over L plus 1 times omega. And that gives you minus 4/3 of omega, or L equals 2. And there's good reason to think that the L equals 2 mode is the only one that's important. Principally, you could have other modes contributing, but this is the one we think is most relevant. Now, the reason that the R mode, as opposed to some of the other oscillation modes that you expect with a neutron star that has this fluid flowing around it, the reason we think that this one is the one that's most susceptible to this kind of an amplification is that the restoring force that gives you that wave pattern is just a Coriolis deflection force. Of a nominally toroidal current. And so that's actually not a very strong force. You know, by the standards of other restoring forces that apply to a neutron star, that's a pretty weak restoring force. And as a result, you end up with a low oscillation frequency. And that's why the spin of the star can easily give you this kind of a scenario. Now, as I mentioned, there are some significant frequency corrections when you do a more accurate model of this process. And once you do that, you really need to be applying a particular equation of state. But those frequency corrections come from higher order rotation terms. The analysis that gives you this relatively simple formula is a low frequency approximation. But if you look at the higher order rotation terms, then some calculations from the Ben Owen group give you the following, that the ratio of FGW over FROT, in fact, is best parameterized as a constant A minus another constant B times the ratio of the rotational frequency of the star over the corresponding Kepler limit, that quantity squared. And of course, that F Kepler limit is going to be dependent on your equation of state, as we discussed earlier in the week. But what they find from an exploration of those possibilities is that A is in the range of 1.39 to 1.57, but then you have this reducing term B that is not well constrained, but is thought to be less than or equal to about 0.195. So if you're carrying out a search for this particular process for, say, a known pulsar where you have the ephemeris, you really need to do a search where you allow for these ranges of A and B parameters, and then hope that you actually see something. So the R mode strain amplitude has a different form from what we saw earlier for quadrupole mass radiation. So let me write that down for you. So the strain amplitude looks like the following. H can be written as the square root of 512, very good sign, 512, pi to the 7th over 5 times G over C to the 5th, 1 over the distance to the source, FGW cubed, as opposed to the square that we saw in the case of mass quadrupole. This parameter alpha I'll come back to in a moment. The mass of the star, radius cubed of the star, and then a dimensionless parameter called J tilde. So let me just comment on those parameters. Well, first let me give you some numbers and I'll comment. So this becomes, plugging in some nominal numbers, 3.6 times 10 to the minus 26 strain amplitude for a star that is 1 kiloparsec away and has a gravitational wave frequency of 1 kilohertz. And this alpha parameter has a value of 10 to the minus 3. And this particular model assumes 11.7 kilometers for the cube of the radius. So alpha is the dimensionless amplitude of the R mode. As I said, there are some arguments that it could be very large, of order 1, but other arguments that it's actually quite small. 10 to the minus 3 is a relatively conservative assumption, although some people would argue it's 10 to the minus 4 or smaller. This J parameter is also dimensionless. And it's actually a functional of the equation of state. If you work it out for an n equals 1 polytrope, just as an example, you get a value of 0.0164. And that's a value that's sometimes used in the literature just as a benchmark, the same way that we use an I naught value for the moment of inertia of a star. It's just an arbitrary choice that we think is in the right ballpark. Okay, so we can look now at the energy loss associated with that. And if you calculate the energy lost from a star that's being dominated by this emission mode, you get minus 1,024 over 25 pi to the 9th g over c to the 7th FGW to the 8th power alpha squared m squared r to the 6th and j tilde squared. So in some sense we get something proportional to the square of h, as you might have guessed. So now let's once again apply the gravitar model the same way we did for mass quadrupole radiation. Let's now apply it to the R mode radiation and see what the relationship between the spin down derivative is and the frequency. So in our gravitar model, where we ascribe all of this energy loss to being the same as the rotational energy loss, what we find is that the first spin down derivative, the gravitational wave frequency, is minus 4,096 over 225 pi to the 7th g over c to the 7th m squared r to the 6th j tilde squared over iz alpha squared and then FGW to the 7th power. Remember, there's a 5th power for the mass quadrupole radiation, giving us a breaking index of 5. Here we're getting a breaking index of 7. And we can also do the same sort of a calculation we did earlier for corresponding spin down upper limit. Again, using the gravitar assumption. And what we find is that H spin down can be written as 1 over D, square root of minus 45 over 8, G over C cubed, IZ, and then FGW dot over FGW. So it looks very similar to what you saw earlier for corresponding spin down limit for mass quadrupole radiation. It's just a slightly different numerical factor inside of that radical. Now I should say that this assumes explicitly that FGW is equal to 4/3 of F rotation, We know that that's not quite right, but it gives you a useful limit to compare against. Okay, so we think this is possibly relevant to actual stellar spin down for known stars out there. That's a very real possibility, again, if you're an optimist anyway. So this is possibly relevant. To neutron star spin down. The R mode dissipation that I alluded to earlier is highly sensitive to temperature. Temperature T of the fluid that's nominally going through this process. And because of that, one gets a potential instability window. Let me draw a crude diagram, and I'll show you something more precise. So horizontally, I'm plotting the temperature in Kelvin of the core of the star, where we think the bulk of this effect would happen. And vertically, I'm plotting the frequency, omega, the rotational angular frequency. And crudely speaking, well, first let me draw some values on the x-axis. So 10 to the 5, 10 to the 8th, so it's a log scale, 10 to the 11th, and so on. There's a window that looks something like the following. There's a horizontal line up here that is defined by the Kepler limit on the rotation. And then there's a dip down here, something like this. And then it goes, ramps up like that and goes back to our plateau. So what we think is happening in here, where you do not get R mode amplification, is that there's a lot of bulk viscosity. And so you don't get an R mode amplification, you don't get R mode spin down. We think down at these lower temperatures, there's a contribution from shear viscosity. In the case of bulk viscosity, you're really talking about nuclear interactions, where you increase the rate of neutrino emission, for example, by compressing the fluid. And here you're talking about more mundane scattering processes, for example, electron scattering. Or you could have core crust boundary issues that lead to dissipation of a current trying to flow through that region. Main thing, though, I want to point out, though, is that if you had a newborn star that started up here, so imagine you have a newborn star right here, and it's spinning close to the Kepler limit at the top of the diagram. So it's got a high rotation frequency, and it's cooling off. So as it cools off, and it cools off relatively rapidly, like so, at some point it moves into the instability window. And once it moves into the instability window where the R mode dissipation has been reduced, then R modes start to build up. And at some point they can build up enough to cause a spin down, and it can be a very rapid spin down. Remember, we have a breaking index of 7 for this process. And so the star then rapidly comes down like so as it continues to cool. It goes into this region of stability and then continues on its way. So that is an interesting possibility for newborn neutron stars, is that as they cool down, they go through an R mode amplification and a very rapid spin down. And so something that might well start at 1,000 hertz or so rotation might end up at a much lower frequency. So this process can spin down a high-speed star to a final frequency that, a rotational frequency, in the ballpark of 100 hertz. And it can do so very quickly once that instability sets in. So let me show you a more precise diagram. This is from Alfred and Schweitzer, wrote this article back in 2014. And it's showing you a more precise calculation for a particular equation of state that follows this model, where we have a star that starts off at a high frequency relative to the maximum Kepler velocity. And then depending on what you assume for the saturation amplitude, if you have a very low saturation amplitude, it might take a while for the R mode to become very important, but eventually it's going to spin you down to this region. Whereas if you had a high saturation, this could happen, this onset could be very quick, and it spins you down also quickly. But the key thing I wanted to point out is that despite the enormous range in these alpha values, they both end up with a relatively narrow range of the final rotation frequency after the spin down. In fact, let me show you another diagram from the same paper where they focus in on that point, where they show those different curves of different saturation amplitudes. Here's amplitude of 1, here's an amplitude of 10 to the minus 4, and now the horizontal axis is the frequency, the cycle frequency. And you can see that over this very large range of assumed amplitudes of the R mode saturation, you end up with a relatively narrow range of the final rotation frequency. And this is a very interesting diagram because, if you look at the young pulsars, you don't see very many, high above this frequency. And this may well explain why we don't see young neutron stars with frequencies much higher than this. So again, if you're an optimist, like those of us in the community, in the continuous wave community are, we look at that and say, okay, that looks intriguing. Let me just mention that there's a particular star, in fact, of great interest now. We already were interested in this star 20 years ago, and then when this paper came out, it increased our interest, and then when another paper came out more recently, our interest increased even more. So this star is J0537-6910. It's an X-ray pulsar. And it could well be in an R mode spin down right now, as we speak. This star is relatively young. It's only 4,000 years old. That makes it an infant by pulsar standards, certainly by millisecond pulsar standards. And there is some evidence of n equals 7 breaking between the very frequent glitches experienced by this star. The star glitches roughly once every 100 days. So let me show you some empirical evidence from this star that supports this idea that maybe there's some n equals 7 breaking. It's not that clean of a pattern. You have to be, again, optimistic to take it too seriously. But this is a plot for that star of the f dot on the, call it nu dot, but it's the frequency derivative on the vertical axis versus time in these modified Julian date days. You can see this star is glitching a lot. But if you look at the behavior between the glitches are these very sharp transitions, you see it here, but then the star tries to get back to some kind of equilibrium. And if you look at the breaking index associated with the second derivative, which is basically the slope of this graph, then you find that this asymptotically tends to approach n equals 7 for the inferred breaking index until it glitches again. It'd be nice if we could have a longer period between glitches so we could see if it really is asymptotically hitting 7 or 5 or 3. But the evidence so far suggests that it's trying to asymptotically reach 7. If that's the case, that's really exciting. That looks like our mode spin down. We'll see how well that holds up as more measurements are carried out. But we pay a lot of attention to that star as a result. We already thought this was an interesting star just because it was so young before we even knew about this potential possibility. And let me finish up by just noting that another candidate for this kind of a process, potentially, is the star that we think is at the center of the supernova remnant. Central compact object, as it's known, from supernova 1987A. That's a star that is remarkably young. It's only 37 years old. Unfortunately, it's a long way away compared to most galactic stars, as in the Large Magellanic Cloud. Unfortunately, so was J0537. And I'll also comment on something I'll come back to tomorrow, namely that our modes may also be important for accreting systems. And I'll explain why that's a possibility when we look at accreting systems tomorrow. Which will be the next topic. So let me end there. Sorry to go so late. Any questions? Let me talk about glitches on tomorrow. I've got it. The mass. The glitch mechanism may be completely separate from the R mode behavior. I mean, I'll talk about glitches tomorrow and possible mechanisms that explain the glitches. Yeah, okay. Well, I'll address that tomorrow. I need to refresh memory on that. Other questions?